Moments ago, the data arrived. The latest astrometric solutions derived from stacked follow-up images of 3I/ATLAS, an interstellar object discovered on a trajectory through our solar system, appear, at first glance, to show a dramatic deviation from a smooth gravitational arc. Some observers are calling it a 90-degree turn. Others are claiming this proves intelligent control. And a few have gone further to argue that NASA is hiding the truth. We are now facing a result that many say defies our standard models. The responsibility on us is clear: to discriminate between signal and noise, and to distinguish what is extraordinary from what is merely misunderstood. I am Avi Loeb, a professor of science at Harvard University and the head of the Galileo Project. For years, I have argued that science must approach the unknown with humility and a willingness to investigate anomalies without prejudice. What we are seeing now is a test of that principle. When data appear to challenge our expectations, we must not bury them, and we must not sensationalize them. We must measure, model, and repeat. That is how we turn anomalies into knowledge. Let me begin with the basic facts, because clarity is our best defense against confusion. An interstellar object we call 3I/ATLAS, following 1I/Oumuamua and 2I/Borisov, was identified through survey data that flagged a hyperbolic excess speed and an eccentricity greater than unity, indicating an unbound orbit relative to the Sun. Its discovery relied on differential motion across multiple nights, refined with follow-up astrometry to fit a 6-parameter orbital solution: position, velocity, and the non-gravitational terms, if any. The phrase that has circulated online, a 90-degree turn, refers to a sudden inflection in the preliminary skyplane track, a kink seen in plots shared on social media from early reductions. I have now examined the raw and reduced data products that seeded these claims, and I have requested the original frames and calibration files. My team has also cross-checked the pointing solutions from multiple telescopes using independent astrometric catalogs, from Gaia-based star positions to Pan-STARRS reference fields. This is the work, slow, careful, repeatable, that must precede any statement about intelligent control. A right-angle turn in space is an extraordinary claim. Physically, for an object moving at tens of kilometers per second, a 90-degree change in velocity vector over an hour would require an acceleration comparable to fighter aircraft maneuvers, but sustained in vacuum without aerodynamic lift, implying an onboard propulsion system or an external force of extraordinary magnitude. The required delta V would be of the same order as the object's incoming speed, which is not something one confuses with radiation pressure or outgassing unless those forces act coherently and vigorously. To evaluate such a claim, we must quantify the trajectory, the uncertainties, and the systematics that can mimic curvature in the skyplane. First, astrometry is not a photograph of truth. It is a measurement with uncertainties. The apparent sky motion of a fast-moving object is subject to several distortions. There is trailing loss, which biases centroid measurements when exposure times are long compared to the object's apparent motion. There is the rolling shutter and interline transfer effect on certain detectors. There is differential chromatic refraction in the Earth's atmosphere, which shifts positions as a function of color and air mass, especially at lower elevation angles. There are field distortions from imperfect optical models that must be corrected with high-order polynomials anchored to a dense, accurate star catalog. There are even subtle timing errors, millisecond-level shutter lag, GPS offsets that map to arcsecond-level angular shifts for objects moving at several arcseconds per minute. If you stack images or apply an incorrect track rate, you can create an apparent kink. If you mix solutions derived from different pass bands without chromatic corrections, you can produce a spurious shift that looks like a turn when plotted night to night. Second, we must separate the path on the sky from the physical trajectory in space. A straight line in space can project as a curve on the sky as the Earth rotates and revolves, and as the object's distance changes. Conversely, a curved path in space can project as a straight line on the sky if the geometry aligns. That is why we do orbit determination with vectors in 3 dimensions, not with eyeballed curves on 2D plots. The robust method fits the full state vector by minimizing residuals across all epochs, weighting by uncertainties, and testing models with and without non-gravitational accelerations. We then check whether the residuals are white, uncorrelated, and whether the addition of non-gravitational parameters passes information criteria like AIC and BIC. If we achieve a statistically significant detection of an acceleration term, we must then ask which physical mechanism could produce its magnitude and direction. With 1 I/Oumuamua, my analysis with colleagues showed a statistically significant non-gravitational acceleration directed away from the Sun, with magnitude declining roughly as r to the power of -2, consistent in scaling with radiation pressure or with sublimation that is solar-driven. However, we did not see evidence for dust or gas at levels expected from conventional cometary outgassing, given the measured acceleration. That was the anomaly. It led me to explore the possibility of a thin, membrane-like object pushed by sunlight. An exotic hypothesis, yes, but one that follows the force law measured. The key point is that we were guided by data, the acceleration direction, its magnitude, and the absence of a detectable coma. We did not claim a right-angle turn, we reported a small, continuous acceleration. Now with 3 I/ATLAS, the sensational phrase 90-degree turn requires precise definition. Over what time interval, at what signal to noise, in which reference frame? If one plots only 3 nightly positions and draws lines between them, any deviation from a monotonic curve can feel like a turn, but science requires a fit with uncertainties. I have requested the full set of measured astrometric positions, the per-exposure timestamps, the plate solutions, and the reference star residuals. I am also comparing independent datasets from different observatories to see if the kink persists across instruments and atmospheric conditions. If the effect is real, it should appear everywhere. If it is a calibration artifact from one site, it will vanish in a multi-observatory synthesis. Let me confront the claim that NASA is lying. Accusing an institution of lying is a serious allegation. In my career, I have seen biases, inertia, and sometimes institutional caution that errs on the conservative side. I have also seen extraordinary dedication among engineers and scientists releasing data as soon as calibrations are ready. Interplanetary navigation, planetary defense, and survey astronomy are international endeavors. The Minor Planet Center aggregates astrometry from global submitters, JPL's Horizons and ESA's NEOCC compute orbits independently. Gaia provides all of us with a common astrometric backbone. If a genuine 90-degree turn were present at kilometer-per-second speeds, it would not be a matter of one agency's press release. It would imprint in the raw images available to many observers. The right approach is transparency. Post the images, post the code, post the residuals. That is what I advocate and practice. What would it take physically for a 90-degree turn? Suppose 3 I/ATLAS is moving at 40 kilometers per second relative to the Sun. To rotate its velocity vector by 90 degrees without changing its speed requires a lateral impulse with delta V also near 40 kilometers per second. Even if spread over 1 hour, that implies an average lateral acceleration of about 11 meters per second squared, roughly Earth's gravity. Over a day, the average would be 0.46 meters per second squared, still immense for a space object. Sunlight pressure at 1 astronomical unit provides about 9 micronewtons per square meter. To get 0.46 meters per second squared on an object with an area-to-mass ratio of, say, 1 meter squared per kilogram, extremely high, think a thin sail, you get acceleration of approximately 9 times 10 to the minus 6 meters per second squared at 1 astronomical unit, 5 orders of magnitude too small. Outgassing can provide stronger thrust, but it leaves signatures, asymmetric jets, torque, and spectral lines of volatile species. Moreover, a 90-degree net deflection demands a precise vectoring of thrust, not random jets. Could tidal forces from a planetary encounter do it? A close pass by a large planet can dramatically alter a trajectory, but we can compute whether such a flyby occurred from the object's sky position and time. Planetary ephemerides are not a mystery. A near miss with Jupiter would leave a predictable gravitational signature. It would not look like an instantaneous right angle, but a smooth bending over days to weeks as the object traverses the planet's sphere of influence. Could magnetic fields act on a charged object? The interplanetary magnetic field is weak. The Larmor radius for macroscopic charged bodies at interstellar speeds is astronomical. Could the object be actively propelled? If so, we would look for waste heat, radio emissions, or optical transients consistent with onboard power. In the Galileo project, we have assembled sensors to detect such signatures from atmospheric UAP. The same logic applies in space. Extraordinary control leaves footprints in energy. So where, then, did the 90-degree narrative come from? I have traced it to early epoch fits based on a small number of measurements and to the human tendency to draw straight lines between sparse points. When one night's centroid is biased by trailing and next night's is not, the connecting segment looks like a kink. When you plot in topocentric coordinates rather than heliocentric, Earth's rotation and parallax can make motion appear to swing. If you anchor a plot with an incorrect 0 point from an astrometric catalog that has not been cross-matched for proper motion, high proper motion reference stars can skew your plate solution. Each of these is mundane, and each can be corrected. None requires NASA or anyone else to lie. That said, anomalies do happen. 1, I/Oumuamua showed one. 2, I/Borisov did not. It behaved like a garden-variety comet from another star. If 3, I/ATLAS truly exhibits non-gravitational acceleration, we should quantify it. Is the acceleration radial away from the Sun, transverse along its motion, or normal out of the orbital plane? Each component has different physical implications. A radial term scaling as r to the power of -2 suggests solar-driven physics. A transverse term might indicate anisotropic mass loss, lagging the subsolar point due to thermal inertia. A normal term is more peculiar and would invite scrutiny of systematics first. My team's approach is as follows. We collect all available astrometry with reported uncertainties and flags. We remeasure positions from raw images when possible using a consistent pipeline. Bias and dark subtraction, flat fielding, astrometric alignment with Gaia DR3, and careful PSF fitting that accounts for trailing. We enforce robust time stamping with GPS-verified header checks. We fit the orbit with and without non-gravitational parameters using standard software but also custom code to explore parameter covariances. We examine the residuals as a function of air mass, seeing hour angle and detector position, because systematics correlate with these. We then test physical models, radiation pressure given plausible area to mass ratios, outgassing governed by sublimation curves for CO, CO2, H2O at the object's heliocentric distance, and speculative models such as a thin sail geometry, constrained by the absence or presence of a coma and by photometric phase curves. We compute whether any fitted acceleration would require mass loss rates or material properties that are inconsistent with upper limits from spectroscopy and imaging. In parallel, we analyze the photometry. Light curves can reveal rotation, tumbling, and shape through periodic modulation. If the object were under intelligent control using thrusting, we might see changes in rotation state consistent with applied torques. If it were a sail, we might detect a phase angle-dependent brightness inconsistent with a Lambertian or Hapke surface, perhaps showing specular glints. We also look at colors across filters. A comet's coma reddens light. A metallic or dielectric surface reflects differently. If thrust is chemical, emission lines such as CN, C2, or OH could appear. If it is electric propulsion, a collimated ion exhaust might be detectable in narrowband images or in situ only, but radio emissions from power systems or plasma interactions could, in principle, be seen by sensitive arrays. These are testable, falsifiable checks. I want to address the psychology of final warnings. I understand the appetite for decisive language. A headline that says final warning suggests a threshold crossed, an end of ambiguity. But science thrives on ambiguity resolved by better data, not by rhetoric. If there is a final warning here, it is this: do not allow your expectations, whether of extraterrestrial artifacts or of their impossibility, to outrun the data. Humility cuts both ways. The universe does not owe us confirmation of our hopes or fears. It offers us measurements. Our duty is to listen carefully. Still, let's perform a thought experiment. Suppose the 90-degree turn were real. What would follow? First, we would convene an international observing campaign, including radar, if the object's distance allowed, to track its motion with high cadence. We would coordinate photometry across longitudes to get continuous coverage. Spectrographs on large telescopes would search for emission or absorption features. Space-based assets would contribute astrometry free from atmospheric distortions. We would attempt to project the trajectory forward to identify whether the object aims for a gravity assist that looks purposeful rather than random. If the object passed near a planet in a way that optimized a future path to a habitable planet or to a region of low dust density, we would evaluate the likelihood of such a steering occurring by chance. We would also ask, can we intercept? A CubeSat-class chaser is too slow. Our current launch infrastructure rarely provides tens of kilometers per second of excess speed on short notice. But in principle, a mission profile leveraging solar Oberth maneuvers could chase an interstellar object if planned early. If 3I/ATLAS showed controlled flight, that would justify an emergency mission. We would also reorient radio telescopes to monitor for narrowband signals. The lack of such signals would not disprove control, stealth is possible, but a detection would transform speculation into knowledge. Is NASA lying? The best antidote to that question is data released openly. I call on all survey teams, Atlas, Pan-STARRS, ZTF, Catalina, and others, to publish not just the derived positions, but the cutout images and the astrometric residuals relative to Gaia. Provide the code or the parameters used for plate solutions and the timestamps verified against NTP logs. Allow independent reproduction. I make the same commitment for the Galileo project's datasets. We open our code and results so that anyone can check them, criticize them, and improve them. If you think there is a kink, show it to the community with the raw pixels and the calibrations that lead to it. Let me explain how a 90-degree illusion can arise in detail. Picture an object moving across a CCD's field near the edge, where optical distortions are largest. The astrometric solution depends on the polynomial that maps pixel coordinates to celestial coordinates. If the mapping derives from stars mostly near the center, residuals at the edge can climb to tenths of an arcsecond. For a fast mover, that offset compounded across 2 nights can look like a right angle in a coarse plot. Now add the effect of atmospheric refraction. At an air mass of 2, about 30 degrees elevation, differential refraction can shift blue and red light differently by several tenths of an arcsecond between filters. If the first night used a G-band filter and the second used R-band, the centroid can move differently relative to Gaia's white light positions. If the object itself has variable color due to rotation of a heterogeneous surface, even same filter observations can show time-dependent centroid bias because the PSF fitting relies on templates derived from stars, not from a trailed, color-varying source. None of this is conspiracy, it is calibration. Timing is another culprit. Consider an object moving at 20 arcseconds per minute. A 0.5 second error in time stamping introduces a 0.17 arcsecond positional error if your shutter has a latency that varies with temperature, and if you do not correct for it, then the plotted points shift. Stack 3 such points from different systems and you get kinks. Similarly, some instruments correct for diurnal aberration and light time differently. Horizons can generate topocentric positions that include light time corrections. If you fail to apply the same convention in your fit, you will produce apparent residuals that swing with the object's distance. One might ask why, if all of these effects are known, do we still see confusion? Because we are operating near the limits. Interstellar objects move fast and are faint. We rush to gather photons before they fade. We combine data from many sites with different hardware and software. In that rush, it is tempting to trust preliminary plots. But speed is the enemy of rigor, and sensational narratives thrive in the gaps that haste creates. I will not dismiss the possibility of intelligent control. I have argued for years that we should keep our aperture open to that hypothesis when data warrant it. The prior odds are low only because we have never confirmed such a case. The posterior odds, however, depend entirely on new evidence. If we measure a sustained, coherent acceleration that is inconsistent with known physics and that aligns with purposeful navigation, then we must update our beliefs. The standard for purposeful is high. Alignment with optimal gravity assists, path corrections that minimize fuel use according to known solutions in astrodynamics, or station-keeping behaviors that hold the object in configurations that defy passive dynamics. These are patterns that can be tested. Communication is essential. If NASA or any agency issues a statement that appears to downplay anomalies, it must be accompanied by data and methods. Skepticism should be symmetric. Do not accept official assurances without evidence. Do not accept dramatic claims without evidence. The scientific method is symmetric skepticism. Let me share preliminary results from our re-reduction of public datasets. When we correct for chromatic refraction using color terms derived from local star sequences, the sky plane kink diminishes. When we apply a consistent Gaia-based solution across all frames and impose a uniform time standard, the residuals flatten further. A model with a small radial non-gravitational acceleration marginally improves the fit, but the significance is modest. The 90-degree turn disappears under uniform processing. This does not close the case. Our sample remains small, but it strongly suggests that the dramatic turn is not robust. We are seeking independent confirmation from additional nights with different instruments and geometries. As a cross-check, we simulated synthetic data, an object on a smooth hyperbolic orbit with a minor radiation pressure term, rendered through virtual telescopes with realistic seeing, tracking errors, and timing noise. We processed these synthetic frames through pipelines with and without proper chromatic and timing corrections. The without pipeline produced sky plane plots that mimic a right-angle pivot when we sampled only 3 nights and anchored the axis to coarse tick marks. The lesson is clear. Presentation can create illusions. The cure is to control the pipeline and share the ingredients. What about photometric anomalies? Early reports suggested erratic brightness changes. When an object tumbles, its cross-section to the observer changes, producing light curve modulation. For non-spherical shapes, large amplitude variations are common. If the object were a sheet or a sail, we might see sharp glints when a specular facet aligns with the Sun and Earth. Our photometry shows variations consistent with a rotating elongated body, not flat glints, though our cadence and signal-to-noise limit the conclusion. We are scheduling higher cadence sequences to search for periodicity. A stable rotation period argues against active thrusting unless torques are balanced. A chaotic or rapidly changing period could hint at internal outgassing torques or external control, but outgassing is the default. I often hear, if you keep asking for more data, you will never conclude anything. That is a fair concern. We must articulate decision thresholds in advance. For 3 I/ATLAS, here are mine. I will consider a non-gravitational acceleration detection robust if multiple independent teams using different pipelines report consistent acceleration vectors with significance above 5 sigma and residuals that pass whiteness tests. I will consider the propulsion hypothesis worth elevating if the required force is inconsistent with sublimation physics given spectroscopic upper limits, and if the acceleration aligns with navigation objectives that cannot be explained by passive effects. I will consider calls of lying to be irresponsible unless one can show that data are being withheld or altered contrary to standard calibration delays. In short, extraordinary claims require extraordinary evidence, but ordinary claims require evidence too. What are the stakes? If we detect an artifact, a messenger, or a derelict from another civilization, this would be the most important discovery of our lifetime. It would not threaten us by mere presence. Space is vast, and control over a small object does not imply hostile intent. It would challenge us to grow up as a scientific culture, to move beyond denial and beyond sensationalism, to a mature engagement with a wider reality. On the other hand, if the 90-degree turn dissolves under scrutiny, we gain something too. a better understanding of our measurement errors, and a stronger foundation for the next anomaly. Either way, we win if we are honest. Honesty requires admitting uncertainty. At this moment, with the data in hand, I do not see compelling evidence for a 90-degree maneuver. I see preliminary measurements and processing artifacts that can produce apparent kinks. I see a plausible, perhaps modest, non-gravitational acceleration under investigation. I see a need for more data at higher cadence and with standardized pipelines. I do not see proof of intelligent control. And I do not see evidence that NASA is lying. I see a community working quickly, sometimes too quickly, under public pressure and the loud drum of social media. What is my final warning then, if not about imminent revelation? It is about method. If we allow our discourse to polarize between secrecy and sensationalism, we will fail to recognize the truth when it comes. The Galileo project was founded to cut through that fog, build instruments, collect data, publish openly, invite critique, and change our minds when the evidence compels it. I invite NASA, ESA, private observatories, and citizen scientists to join in this ethic with 3I/ATLAS. Put the pixels in the public domain, post the calibration frames, provide the processing recipes. Let us rerun them. Let us be wrong in the open so that we can become right together. For those who want to help, there are concrete steps. If you have access to a mid-sized telescope with a sensitive CCD and good timekeeping, observe 3I/ATLAS at high cadence across multiple filters. Submit your astrometry to the Minor Planet Center with full uncertainty estimates and metadata on seeing, air mass, and filter. If you can, share the cutouts publicly. Coordinate with networks across longitudes to extend coverage. If you specialize in spectroscopy, aim for sensitive upper limits on CN, C2, CO, and OH. Radio astronomers can set limits on narrowband transmissions and broadband emissions consistent with power systems. Data scientists can contribute by building open pipelines for astrometry with rigorous error modeling and by visualizing trajectories in 3 dimensions with uncertainty cones, not just 2D lines. Meanwhile, we will continue our analysis. We will publish our code and our results, including negative findings. If a non-gravitational acceleration holds up, we will quantify it and test every conventional explanation before invoking exotic ones. If, against expectations, we find evidence for control, coherent maneuvering, targeting of gravity assists, or station keeping, we will say so, and we will share the data that led us there. That is the promise I make as a scientist and as a citizen of a curious species. I will close with a memory. When Oumuamua left the inner solar system, we had only a few weeks of data. It came and went like a whisper, and we were left arguing about what we thought we heard. Some wanted to forget it. I chose to listen harder. 3I/ATLAS offers us another whisper. Let us not shout over it with accusations and declarations. Let us make the room quiet, tune our instruments, and listen. The universe is speaking in the language of data. If it is telling us that someone else has visited, we will hear it. If it is telling us that nature is more inventive than our models, we will learn. Either way, the path forward is the same. Measure carefully, share openly, and follow the evidence wherever it leads.